In this video, we will be taking a look at adjacency matrix, which is a method of representing graphs in memory. So let's begin by taking a look at this directed unweighted graph. So the way this graph would be represented in memory is in a 4 by 4 matrix. But how do we know that it's 4 by 4? Because the number of vertices in this graph uh, is equal to 4, and therefore we have a 2D array, which is a matrix of 4 by 4 dimensions. So here, why there are zeros and ones here is because there is no edge between 0 to 0. So that means there is no self loop. So we will only include a 1 if there is an edge, a direct edge from a source node to a destination node. So we will read it like this. So there is no edge from 0 to 0. So that's why we have a 0 here. There is an edge from vertex 0 to vertex 1, so there is a 1 here. There is no edge from vertex 0 to vertex 2, so there is a 0. And there is a direct edge from vertex 0 to vertex 3, so there is a 1. As we can see, there is a direct edge from vertex 0 to vertex 1 and a direct edge from vertex 0 to vertex 3. Similarly, in other rows, we can check whether there are any nodes where there are where there are basically direct edges. So over here, there is no direct edge between vertex 1 and vertex 0. So there's no edge from vertex 1 to vertex 0. From vertex 1 to vertex 0, there is no direct edge. So we put a 0 here. There is no direct edge from vertex 1 to itself, so that means there is no self loop, so that's true here, so we have a 0 here. And similarly, there is an edge from vertex 1 to vertex 2, as we can see here, from vertex 1 to vertex 2 there is an edge, so we go to 1 2 and then there is an edge, so we put a 1. So similarly, we will fill the rest of the matrix with this way of judging whether there's an edge or not. As we can see, there's a pattern here. If you look at this diagonal from top left to bottom right, all of it is filled with zeros, which means there are no self loops. You can see there is no loop from 1 to 1, no self loop from 0 to 0, no edge from 2 to 2, no edge from 3 to 3. So that means there are no self loops. That's why the diagonals are filled with 0. And adjacency matrix is the best way to represent dense graphs. Dense graphs, as we have seen before, is basically like the graphs which have the number of edges in the order of the number of vertices square, or basically a graph with a lot of edges. So when that's the case, then we prefer using adjacency matrix, and that's the best way to represent dense graphs. And we can see here the number of rows and number of columns is equal to the number of vertices. Now let's move on to representing undirected graphs, and they're also unweighted in terms of adjacency matrix. So if you see here, the number of ones we have in the adjacency matrix is basically the number of edges that exist in the actual undirected graph. The reason being, undirected edges are basically bidirectional in nature. So although we see only one edge between 1 and 3, it basically represents that there is an edge between vertex 1 to vertex 3. That's why we have a 1 here. And also there's an edge between vertex 3 and vertex 1. So we have an edge over here. We have a 1 over here. And similarly, there is an edge going from 0 to 3 and 3 to 0. So we have 1 here. So 0 to 3. So we have a 1 there. And from 3 to 0. So we have a 1 there as well. And again, we don't have any self loops. So this diagonal from top left to bottom right is filled with zeros. Now let's take a look at adjacency matrix for undirected weighted graphs. So suppose there were weights given to this graph. Let's say there is for these edges, so the edge between 1 and 3 connecting vertices 1 and 3 has a weight of 2, and the edge connecting the vertex 3 with vertex 2 has a weight of 3, and this edge uh, has a weight of only 1, and this edge has a weight of 7 and 8 and 10. So how would we represent this within the adjacency matrix? So of course, 0 to 0, there are no self loops, so the diagonals continue to be zeros. But from 0 to 1, if we look from 0, between 0 and 1, the edge has weight of 8. So instead of 1, we will end up having 8. And because we have filled 0 to 1, we need to go for 1 to 0 as well. There is an edge, and we will call it as 8. Basically, there is an edge with weight 8. Now let's look at 1 to 3. So 1 to 3, there's an edge of weight 2. So 1 to 3, there's an edge of weight 2. And from 3 to 1, from 3 to 1, again it's the same edge with weight 2. So let's fill it. 3 to 1, and there's an edge with weight 2. And similarly we can do for the other vertices in this graph. Now let's move on to sort of a different scenario where before we used to have the vertices to be 0, 1, 2, 3, which were exactly the indices of the matrix if we saw. Because the arrays basically start from the indices start from 0, 1, 2, 3, and they're zero based, so it was easy for us to represent it using adjacency matrix. But now there is basically the vertices have A, B, C, and D as the data instead of 0, 1, 2, and 3. So in this case, the solution is pretty simple. We'll make use of a hash map, and the keys will be basically the vertex names, and the values will be the indices that the corresponding vertex maps to. So, for example, to say that there is no self loop for the vertex A, so there is no edge between A and A, we can do adjacency, which would be the name of the matrix. So name of the matrix, and then within we can get map of A, and then map of A again, because we are saying this is the source node, this is the destination node. There is no edge going from A to A, so we put 0. So what will happen is we'll go map of A, that's 0, and basically this will be equivalent to saying adjacency of 0 and 0. So basically you go here and put a 0 there. And similarly for adjacency of map of A, map of B, so you get 0, comma 1 or 0, 1, and you go to 0, 1, you put a 1. So, and so on. You can do this for the rest of the graph. And basically, to wrap things up, we can look at the time complexity for various operations that can be done on the adjacency matrix. To check whether an edge exists between a source node and a destination node, it takes constant time, because even if we are using a hash map, remember that accessing a key's value within a hash map takes constant time. So even this operation would basically take, basically assigning an edge or removing or inserting an edge or checking for an edge. All of it would take constant time. And as it's mentioned here, even removing and adding edges takes constant time. And to look for all adjacent vertices or neighbors of a vertex, it takes big O of the number of vertices. So what are adjacent vertices? So if we look at vertex A, what are all its adjacent vertices? Basically, adjacent vertices are the vertices which are directly connected to A with the direct edge. So basically, a direct edge goes from A to B, a direct edge goes from A to D, and a direct edge goes, and that's it, right? So basically, all the adjacent vertices of A are B and D. That's why over here, if you look at A's corresponding index, which is 0, we have 1 at the column representing B and column representing D. We have 1 and 1. And similarly, all the adjacent vertices of B being C and D, because there's a direct edge going from B to D and B to C. Basically, we have 1 and 1 in the uh, adjacency matrix. So basically, to look for all adjacent vertices, it takes big O of the number of vertices time, because as we remember, the number of columns and the number of rows, right? They are basically the number of vertices. So here we are only concerned about the number of columns, and the number of columns is equal to the number of vertices. And if you want to check all the possible adjacent um, vertices of B, you have to go from left to right, and you would have traversed all the columns. So that's going to take big O of the cardinality of set V time, which is nothing but big O of number of vertices time. And as we have seen, number of columns and number of vertices, number of columns and number of rows is equal to number of vertices. And if we look at the total space, it's basically going to be number of vertices square. That's the amount of space this whole adjacency matrix is taking. And this is good to represent dense graphs because they have a lot of edges. But when we are looking at sparse graphs, it's not so great because the sparse graphs have minimal edges, and this is not the best way of representing sparse graphs at all. That's why it's pretty inefficient. And adding a new vertex will take big O of the number of vertices square time, because here, when we already have a vertex of 4 by 4 in this case, if we want to create another, if we want to add another vertex, let's say it's E, then we would have to basically create a whole new matrix, and now it will be a 5 by 5 matrix, and populate that matrix with all the values of the previous matrix, and add the edges, or remove the edges as per the need of the new matrix. So that is it for adjacency matrix. Thank you all for watching, and see you all in the next video.